How does deep learning move from theory into practical systems you use and depend on? It has proven effective in computer vision, speech processing, text analysis, and graph processing. You are about to trace the techniques and applications that make those real-world uses possible. Across these domains, deep learning tackles complex challenges with domain-specific methods. Computer vision draws on convolutional networks and vision transformers. Speech and text rely on recurrent networks, transformers, and attention, while graph processing uses graph neural networks to model nodes, edges, and relationships. In computer vision, convolutional neural networks support image classification, object detection, and segmentation. Key architectures include ResNet, YOLO, and UNet, while vision transformers treat images as sequences of patches. Applications include diagnosing disease from X-rays or CT scans, detecting pedestrians and traffic signs, segmenting medical images, and facial recognition. Attention mechanisms help models focus on the most relevant parts of an input. In vision, they improve object recognition and feature extraction, either alongside convolutional networks or within vision transformers. Self-attention captures global dependencies, spatial attention highlights important regions, and channel attention prioritizes the most useful feature maps. A convolutional neural network combines several core parts. Convolutional layers extract spatial features with filters, pooling layers reduce spatial dimensions, fully connected layers support classification, and activation functions such as ReLU, sigmoid, and TON add nonlinear transformations. Classic architectures include LeNet, AlexNet, VGG, and ResNet. Transfer learning reuses a pre-trained model on a new dataset to reduce training time and improve performance. A model such as ResNet, VGG, or Inception can be fine-tuned for a smaller task-specific dataset. This avoids training from scratch and builds on general features already learned. Implementation begins with loading and pre-processing data through resizing, normalization, and augmentation, then splitting it into training, validation, and test sets. Next comes model design, training, evaluation, and deployment. Evaluation can use accuracy, precision, recall, and F1 score, while deployment may use quantization or pruning. Speech processing uses recurrent neural networks to model sequential data for recognition and synthesis. Transformer-based models such as WAV to VEC and Whisper use self-attention for efficient speech-to-text processing, while convolutional networks extract features from spectrograms. Applications include transcription, text-to-speech, and speaker identification. Speech recognition converts audio signals into text by processing temporal dependencies in audio data. Standard recurrent neural networks capture sequence patterns, while LSTM models address vanishing gradient problems and GRU models reduce computational complexity. Applications include virtual assistants, call centers, and real-time captioning for accessibility tools. Machine translation converts text from one language to another while maintaining semantic and syntactic integrity. Encoder-decoder recurrent networks process the input sequence into a context representation, then generate translated output. Attention mechanisms improve this by focusing on relevant input parts, and transformer models now support state-of-the-art translation systems. Real-time translation systems combine speech recognition, machine translation, and speech synthesis for multilingual communication. They support uses such as captioning and spoken output in international conferences, live translation in video conferencing, and language learning tools. Main challenges include accuracy, latency, and the need to use visual and contextual information well. 0, 20, 30, 405. Text analysis draws heavily on transformer models and recurrent models. BERT is pre-trained for natural language understanding tasks such as question answering, while GPT generates coherent and contextually relevant text. LSTM and GRU models handle sequential data, and attention mechanisms improve focus on relevant input for translation tasks. These techniques support a wide range of text applications. Sentiment analysis can examine customer reviews for brand sentiment. Machine translation supports multilingual translation. Text summarization condenses large articles into concise summaries, and chatbots provide automated responses in customer service settings. Generative models create synthetic data for training, testing, and simulation. They are useful when data is scarce or imbalanced. The main techniques here are variational autoencoders, generative adversarial networks, and diffusion models, each offering a different way to generate new samples from learned patterns. Variational autoencoders encode data into a latent space and decode it to generate similar samples. They produce smooth and continuous latent spaces, which makes them useful for generating variations of data. Applications include image reconstruction, data augmentation, and anomaly detection, with stable training as a notable strength. Generative adversarial networks train a generator and a discriminator in opposition. The generator creates synthetic data, while the discriminator tries to distinguish real samples from synthetic ones. This can produce high-quality and realistic outputs for image synthesis, style transfer, and data augmentation, though instability and mode collapse remain important weaknesses. 02, 03, 04, 05. Diffusion models add noise to data during training, then learn to reverse that noise process to create new samples. They are known for diverse and high-quality outputs. Applications include text-to-image generation, video generation, and augmentation for imbalanced datasets, although they can be computationally intensive and slow to generate. Choosing among these models depends on task needs such as output quality, diversity, interpretability, and computational constraints. Development typically includes data preparation, model design, training, evaluation, and application. Evaluation can use inception score, Fréchet inception distance, and reconstruction loss before synthetic data is used in practice. Graph processing focuses on data structured through nodes and edges. Graph neural networks extend neural methods to this non-Euclidean setting, and graph convolutional networks aggregate information from neighboring nodes. Applications include social network analysis, recommendation systems, knowledge graphs, and drug discovery based on structured relationships. Graph neural networks for graphs. They aggregate from neighbors and propagate information across nodes and neighbors to capture global structure. Important types include graph convolutional models, graph attention networks, and message-passing neural networks. Drug discovery in graphs, model protein-protein interactions to study pathways and mechanisms, examine relationships in medical imaging, and uncover patterns in genomics. These uses help disease research, targeted therapies, and predictions of efficacy or toxicity. Implementation starts by representing the dataset as a graph with nodes and edges, then encoding node and edge features. After selecting an architecture such as G, C, N, GAT, or MPNN, training can be supervised or unsupervised. Evaluation may use node classification accuracy, edge prediction, or graph-level task performance. You have seen how deep learning techniques map to real-world problems across vision, speech, text, generative modeling, and graph analysis. The methods differ, but each is tied to practical tasks such as classification, translation, synthetic data creation, and relationship modeling. That is how deep learning turns specialized architectures into useful applications.